Hello and hi everyone. We will be presenting our project, which is the title is Inner Peace Meter, Monitoring Stress Level Through Galvanic Skin Response. And our presenter is Siti Syahada, Kuhan, Noshifa Nadira, Iza Aidila, and Kumaresan. So our presentation will cover about the introduction to galvanic skin sensor, literature review, highlights, methodology, result and discussion, and lastly is a conclusion. So first, let's start with the introduction. Galvanic skin response, also known as electrodermal activity or EDA, it measures changes in skin conductance caused by the activity of sweat glands. So when people experience emotional arousal such as stress, fear, or excitement, our sweat glands become more active, and this increases the electrical conductance of the skin, which is controlled by the autonomic nervous system, specifically the sympathetic branch. Now let's move to the historical background of GSR. The concept of GSR dates back to the late 19th century. In 1888, Charles Ferrer discovered that changes in skin conductance occur due to external stimuli and emotional responses. Around the same time, Ivan Tarchanov introduced the idea of the psychogalvanic reflex, that connecting electrical skin response with emotional states. Then in the early 20th century, Carl Jung used GSR psychological studies to understand subconscious processes. By the mid-20th century, researchers established that GSR is closely linked to the activity of the sympathetic nervous system, and making it useful in stress studies, cognitive research, and even lie detectors. And in the recent decades, which is now, GSR technology has advanced significantly. Modern sensors are now portable, wireless, and integrated into wearable devices, enabling their use in healthcare, gaming, and even human-computer interaction. So the objective for this project is to design and test portable low-cost GSR sensor that are more sensitive and user-friendly for real-time monitoring arousal responses. Next is to assess the role of GSR in diagnosis and follow-up on mental health condition. And the last is to investigate the effectiveness of GSR-based biofeedback methodologies in improving self-regulation related to stress and emotional states, and focusing on neurorehabilitation and therapeutic interventions. Next, let's discuss the relevance and feasibility of this study. So GSR is highly relevant today due to the rising prevalence of stress and mental health issues worldwide. As a non-invasive, affordable diagnosis tool, GSR provides a practical way to monitor emotional and psychological states. So the application extends beyond healthcare to fields like gaming, wearable technology, and IoT. In a term of feasibility, this research is supported by several factors, which is the first is affordable components like Arduino microcontrollers and Bluetooth make it easy to design GSR sensors. And next is decades of research have validated the effectiveness of GSR in measuring emotional arousal. GSR sensor also are lightweight, portable, and energy efficient. And the last is the use of low-cost materials ensures scalability and commercialization.
Assalamualaikum, my name is Siti Nur Syahada binti Muhammad Afendi, and in this video presentation I will be presenting the next chapter, which is literature review highlights for galvanic skin response. The first subchapter is electrodermal activity, or in short EDA, and stress assessment. So what is EDA? EDA measures how your skin reacts to emotion or stress by tracking your sweat gland activity. It reflects how your body responds to stress or emotions through the changes in skin resistance. So how it is measured? There are two methods. The first one is endosomatic, where we measure the skin natural electrical signal without adding any external current. And exosomatic uses a small electric current to measure how well your skin conductivity. And this method is most commonly used by the psychologists. So EDA has two main components. The first one is skin conductance level, which is your SCL. It tracks your overall or long-term changes in your emotional state. The second one is skin conductance response, or SCR. It tracks quick, short-term changes when something specific like stress or a loud noise triggers an emotional state. Relevance to stress and emotions. So increased stress or anxiety will produce high sweat secretion, which then increase your conductivity and lower your skin resistance. For relaxed states or satisfaction, your body will produce a lower sweat secretion and then decrease your conductivity, which increase your skin resistance. Next subchapter is galvanic skin response application in psychiatry. So we found that sweating linked to your stress, anxiety, and also emotional arousal, which is mentioned just now, whereby when you are in stress mode, when you are in a stress state, your sweat secretion will increase. And if you are in a relaxed state, your body will produce a lower sweat secretion, which then make your skin resistance higher. So application for GSR in psychiatry is quantitative measure of sympathetic activity in psychophysiology. So we also found that the psychologists are using GSR for diagnosing disorders such as anxiety, depression, bipolar disorder, and schizophrenia. Next, we are still looking at the same subchapter. So we also apply this GSR in psychiatry for clinical insight. For example, lower SCL is displayed in depression, while higher in mania, and stronger SCR in depression for emotional trigger, for example, fear. And if someone has schizophrenia, their SCL reading will be high for positive symptoms like hallucinations, and reduced SCR for negative symptoms like fear. Also, the GSR is used for diagnostic utility as to identify disease stages, severity, and recurrence likelihood. Next is galvanic skin response in detecting emotional stress. So modern application in psychiatry and psychophysiology, GSR helps to detect your emotional stress, your pain, if you have any epilepsy, and sleep recovery, etc. Also, GSR helps with signal processing advancement. For example, beyond tonic, or tonic means, in other words, steady, and your phasic or your short-term components. And it also provides mathematical measure to improve your data analysis. So to conclude the whole chapter for literature review, we can conclude that GSR helps to bridge the physiological responses and also your psychological states, as SCL and STR offer insight into your emotional and your mental health, as mentioned previously. Also, we can apply it for diagnosing and managing stress, which is we try to implement in our project. It also can diagnose anxiety, depression, bipolar disorder, schizophrenia, and many more. And also helps to advance in technique, have extended clinical and research use. So that is all from me. Thank you.
So now I will present about the methodology of our project. So there are three main components that can be covered in our methodology, which are hardware development, software development, and testing and calibration. So in our hardware development, we have used the Arduino board, LED indicators, and the GSR sensor in order to make it fully work for our project. While for our software development, we have used a coding to integrate with the hardware so that the sensor can be used. And next, testing and calibration. We have tested and calibrated using our teammates itself by taking different readings and setting the baseline for the sensor. So the reading will be different for each of us, and from that we will set a reference value in order to check whether the value raises or falls down. For hardware development, we have used GSR sensor, Arduino Uno board, LEDs, and resistor. The GSR sensor captures the electrical conductance of the skin to measure stress level. The Arduino board, it serves as the microcontroller for processing the GSR data, and LED, we have used three LEDs, red, green, and yellow. Red, which indicates a rise in GSR reading, while green indicates a fall in GSR reading. The yellow indicates a stable GSR reading. For resistor and wires, it's just to complete the circuit and for proper electrical connections and circuit safety. While for software development, we use the we use Arduino IDE to code for our project. So the code structure, we have done a few uh, flow in order to complete the code, which we initialize the pins for the sensor and LED. We declare the pin and the LED, and serial monitor was enabled for debugging. Then data reading. The data was read through the serial plotter in Arduino IDE itself. So we saw the graph over there and we read the data from it, data processing. So from the graph itself also, we have recorded the data manually. We have read the data manually, so we can study about the different people of GSR readings. We couldn't do it automatically since the GSR reading is not the same for everyone. So for each person, we have to read the data manually. And the last one is output control, which based on the analysis, specific LED were activated to provide visual feedback. As I explained before, red LED is used to measure the rise, yellow LED is for stable reading, and green is for a fall in the reading. So I have shared a snapshot of coding into the slide also. For testing and calibration, we have taken care about a few things, which are sensor placement, baseline calibration, and sensitivity adjustment. So the sensor placement, we place the sensor on table like that. So once the volunteer has worn the sensor, they have to put their hand on the table so that it doesn't shake, it doesn't move, in order to reduce the noise in the sensor. So baseline calibration, volunteers their relaxed state readings were used to establish a baseline. So that baseline is the reference value. So once if the reading goes up, a red color LED will be triggered, and once the value goes down, a green color LED will be triggered. So next, testing. Monitored stress level over 1 minute with LED indicators is used. So it was giving us the real-time feedback of the person's reading. Next is sensitivity adjustment. So we were using a moving average filter to reduce noise and refine threshold through iterative testing. Now I will show you the demonstration of our project in the following video. Hello guys, so as I explained before, this is the setup of the hardware. So we have the Arduino board, we have the LED indicators, and this is the GSR sensor. So after we are wearing the GSR sensor, we have to put our hands. The placement should be on table or any flat surfaces in order to reduce noise in the sensor. So as you can see, the yellow color LED indicator is lighted up, which means my reading should be quite stable. So you can see the reading here is reading as stable. So I had a peak over here, so which means during that time the red color indicator should be lighted up. And this is the coding for our project. So the coding which sends the signal into the Arduino, and the Arduino gets the input from GSR sensor, the signal. This is the signal, and it reads into the graph. So that is how basically our project works. So as you can see, the baseline has some fluctuations, so it is reducing and increasing. So right now I can be considered as more calm and more peaceful since the reading has gone through down.
Hello people, let's look at the results and discuss their application. During the testing, we had a sample reading of a volunteer and we observed a clear patterns of a graph. The graph given shows the GSI in microsieverts against the time in a millisecond. From the graph, we observe that the lines representing the reading of a stress level, whether they are high, low or stable. If the person is stressed, the graph tend to rise, while they are calm or reduce stress, the graph will fall. The horizontal line represents a stable condition, whether it can be the person is stressfully stable or they are stable in a calm situation, something like that. Yeah. So next, the LED system effectively communicated the stress trends in a real time, which means the red LED light up during the stress inducing activities, while the green LED activated during relaxation exercise or the person in a calm situation. The yellow LED served as the stability indicator, as I mentioned earlier, when no significant changes were detected. We also analyzed the stress trends quantitatively. The frequency of LED activation over a minute provide a measurable indicator of stress level. For example, a volunteer with a frequent red LED represent their more stress, something like that. While those with more green lights represent they are not so stressed, or they are in a calm or relaxed in a situation. This simple yet effective method allows for clear categorization. The system performance was enhanced by implementing a moving average filter in the software. This significantly reduced the noise and stabilized the GSR reading. Additionally, we also calibrated a threshold of 5, which gives the accurate detection by differentiating the stress changes in a small fluctuation. Based on the discussion, the device provides the accurate result by averaging the GSR readings, which reduces noise and make the data more reliable. However, different people have a different baseline of GSR levels, so we had to calibrate the system individually for each person to ensure the results of the readings were accurate. The LED lights were very effective in this design, like meaning that volunteers can easily understood what the red light meant, like they are stressed, and the green meant as relaxation or calm, and yellow showed like no change, or in other words it is stable, something like that. So this real-time feedback made the system user-friendly and also a practical in a daily life, something. Yeah. Of course, there is limitation. One limitation was the need to calibrate the system for each person, which could be automated in a future iteration. We also noticed that the way the sensor was attached or pressed on the skin sometimes affected the readings. Adding a better attachment option or pressure sensor could fix the problem itself. And also we noticed that the environmental factors like temperature and humidity slightly influence the result, whereby, like, for example, when the environment is in a high temperature, like in hot weather or something like that, the person will tend to sweat, so it could affect the reading as well. And also the few challenges we faced during the testing is like, one of the challenges was placing the sensor on a fingertip. If the sensor is placed on the knuckle of the finger, it won't show accurate reading. So it's better to place the sensor in the fingertip. And the other challenges was the like moisture in our skin. So we asked the volunteer to dry up their hand first before doing the testing.
Hello, my name is Iza Idila binti Azman. My matrix number is BK22110-299. So today I will be presenting the last chapter of our thesis, which is chapter 5, conclusion. A portable galvanic skin response GSR sensor prototype was successfully developed in this study to track stress levels. In order to satisfy the increasing need for instruments that can accurately identify stress, we set out to create a device that is portable, inexpensive, and simple to use. The GSR sensor measures change in skin conductance caused by the autonomic nervous system, offering a reliable and non-invasive way to assess emotional and psychological arousal. This prototype stands out with its advanced features like Bluetooth connectivity for wireless data transmission and real-time monitoring. Validation tests show that the prototype is highly sensitive and accurate, providing results comparable to commercial GSR sensor. So this proves the device reliability in detecting stress response, making it suitable for both clinical and personal use. Our research also enhanced our understanding of electrodermal activity, EDA, as a psychological marker for stress. It illustrates the practical application of GSR technology by showing how it may be incorporated into wearable health monitoring devices, stress management program, and biofeedback therapy. This GSR sensor has the potential to be a useful tool for addressing mental health issues and fostering emotional well-being because of its low cost, mobility, and robust performance. In the future, we believe that the sensor's performance might be improved by combining it with cutting-edge software, such as smartphone apps, to enable more thorough data analysis and user interaction. Its adaptability may also be further demonstrated by investigating its application in other fields, such as pen monitoring and cognitive load evaluation.